Before we start bringing new and complicated exponents into the mix, let's review the properties that we know for positive integer exponents. And the first thing that we know is just what a positive integer exponent means. It just means m copies of the number x, all multiplied together. So, to cite a specific example, 5 to the 7th is 7 copies of the number 5, all multiplied together. And I could multiply that by hand, or I could do it in a calculator. So if I multiply together 7 copies of the number 5, I get 78,125, which is in fact what my calculator gives me for 5 to the 7th power. We all know this property of exponents, but it's actually this property that all of the rest of the properties of exponents come from. The next property we know applies to taking a power of a product. Multiplying two numbers and raising the product to the mth power is the same as raising the first number to the mth power and then raising the second number to the mth power and multiplying them together. Why? Well, xy to the mth power means x times y times x times y times x times y, and that's m copies of each. M copies of x, m copies of y. Rearranging with the commutative property, we have m copies of x times m copies of y. So that's just what you think it is. It's x to the m times y to the m. Same holds for division. I'm not going to show it to you. X divided by y to the mth power is x to the mth power over y to the mth power. And this is for any numbers x and y where y isn't 0. Next we're going to meet some properties that involve different powers of the same number. For any number x, x to the m times x to the n equals x to the m plus n, right? Because what do we have here? X to the m times x to the n, that'll be m copies of x times another n copies of x, which, when we put them next to each other, clearly give us m plus n copies. And so this is obviously x to the m plus n. But this tells us something has to be true. For any x that is not 0, x to the 0 has to be 1. Why? For any x that's not 0, clearly x to the m is the same as x to the m plus 0, because, well, m plus 0 is the same as m. So that's the same as x to the m times x to the 0. If x is not 0, then x to the m isn't 0. So, dividing by x to the m, I'm left with 1 equals x to the 0. X to the 0 equals 1 is not arbitrary. It has to be this way to make the exponent rules work for 0. And now I'd like to say what we mean by a negative number power of x. If n is a positive integer, what will x to the negative n have to be? Well, I know that x to the n times x to the negative n must be x to the n minus n, which is x to the 0, which is 1 for x not 0. For x equals 0, 0 to the 0 is undefined. Just a quick note. Back to our regularly scheduled negative exponents. But we also know that x to the n times 1 over x to the n has to be 1. And so we can infer that if we want the exponent rules to work the way that we want them to, x to the negative n has to equal 1 over x to the n. And now we can also come up with dividing exponents without any resort to kind of fiddling around saying where things are going to be. For any integers m and n, positive, negative, or 0 now, we have that same rule that we had before, and we can also say that x to the m divided by x to the n, that's the same as x to the m times x to the negative n, but that's just going to be x to the m minus n. So we also have a rule for division. The last rule we're going to look at is rules for taking a power of a power, and this is going to turn out to be really important to us in a moment. Well, I'm going to just show you this for positive integers, and then you can generalize this to all integers on your own. X to the m to the n is x to the m times x to the m times ... x to the m. This is going to be n copies. And why did I write these out in rows? Because now I'm going to write out x times x times x ... times x times x times x times x ... times x times x times x times x ... times x. So I have n rows of x's with m x's in each row. Well, I know what that is. If I have n rows and m columns, this whole block contains m times n copies. So x to the m to the n must be x to the m times n. And those are all of the exponent properties that we're familiar with so far. Just to have a handy summary for reference, for integers m and n, and numbers x, y, neither one of which is 0, we have the following properties. X times y to the mth power is x to the mth power times y to the mth power. And also the analogous property for division. If I multiply together two powers of x, I'll get x to the power of the sum of the exponents. If I divide, I'll get the difference of the exponents. If I take a negative exponent, that's the reciprocal of the positive exponent. This applies, of course, even if n happens to be a negative integer. So I can also write this as this, and putting that together with this property, I can get this other way of thinking about negative exponents, should it become necessary. And then finally, I have that power of a power rule, and the rule about anything to the 0th power being 1. And that's it. 1, 2, 3, 4, 5, 6, 7 different properties of exponents. That's really all that we need to know about exponents.